Okay, let's go to number 8. We are given the position function of an object, projectile maybe. S of t is 3t minus 1 in quantity to the third power. And we are to find its velocity at 1 and the acceleration when t is equal to 1. So what is that? Well, the velocity, as you know, is the derivative of the position function. So for this, you apply the chain rule. It's 3 times this quantity to the squared times the derivative of the inside function. So that will make this 9 times 3t minus 1 squared. If you evaluate this at 1, you get 9 times 3 minus 1, that's 2, 2 squared, that's 4. That's 36, okay? So the velocity at 1 second, or when t is equal to 1, is 36. And if you have to give, well, we're not given the units, but it's going to be a unit per square, per second, right? Assuming that t is in seconds. All right, and then the acceleration, a of t is the second derivative of the position function, or the first derivative of the velocity function. So you take the second derivative. So let's take the derivative of this thing here. So this becomes 9 times 2, that's 18, 3t minus 1 to the first power, times the derivative of the inside function, which is 3. So that's 54 times 3t minus 1. And so the acceleration when t is equal to 1 is 54, and then 2, or it's 3 minus 1, which is 2. So it's 108. And so this will be the unit of length per square second. That's what happens when acceleration. It's basically unit per second, right? So this is how fast the velocity is changing every second. All right, so these are pretty simple questions. You just have to know that the first derivative is the velocity, the second derivative is the acceleration. Okay, number 9 is about the absolute maxima and minima. I want you to know first, this is, we have 4 questions, but this question is really not about critical points, okay? It's more about, do you know what we mean by absolute maxima and minima? And clearly, an absolute maximum is the highest y value, the greatest y value in its domain, and the absolute minimum is the least value that the function takes in its domain, right? And they are not guaranteed to have absolute maxima or minima, all right? It is, a function does have both of these if the domain is closed and bounded and the function is continuous. That's called the extreme value theorem. But, well, okay, we'll see how that applies. The first function is y is x squared minus 2. So you should know what this function looks like. Right? Just try to graph this. It's x squared is like that, minus 2 makes it lower by 2 units. So the graph will look like this. Now this value, the zeros are plus or minus the square root of 2. That's the kind of function. It doesn't really matter. Does it have an absolute maximum? No, because it goes continuing to go up to positive infinity. So no absolute maximum. But there is an absolute minimum because clearly there's a lowest point, and that's going to be negative 2. Okay. Remember, you are to give the y value if you are asked to find the absolute minimum. If you are asked where does the absolute minimum occur, or at what x values does the absolute minimum occur, then you would say the absolute minimum of negative 2 occurs at x is equal to 0. Okay, it's right here. That is what you can say. You can also say things like, the absolute minimum occurs at x is equal to 0. But if you're simply asked for the absolute minimum value, that would be negative 2. Okay, part B. Y is x cubed. You should know what the graph of this looks like also. It's that sort of a nice looking curve that is a hook curve, symmetric with respect to the origin and all that. Clearly, this goes up to the infinity, down to negative infinity, no absolute maximum or minimum. Okay, just because it just goes up to positive. If you say there is, this absolute maximum is some number k, I can say, no, I can go bigger than that, right? There are x values where y is k plus 1, k plus 2, and so on. So there is no absolutely highest point of this graph. That's basically what that means. C is -3 sine x. This could be a tricky thing, right? So the sine function goes like this. -3 is more like this, right? So the highest point is 3, the lowest point is -3, right? And it happens at a bunch of these points. But regardless of how many times it happens, if the highest point, if the highest y value, if the largest value of this function is 3, then that is the absolute maximum. Absolute maximum is 3, and that occurs at points like -π/2 and negative, let's see, what is that? This is, so that's π/2, pi, 3π/2, and so on, right? The question doesn't ask where these absolute max and min occur, so we don't have to worry about this. We can just say the absolute maximum is 3, and the absolute minimum is -3. Okay, that's how you can answer this question. The last part D of this question is 2e to the x. The exponential function, even though it's multiplied by 2, well, basically it's the same shape. It grows exponentially. All right, so clearly as x approaches infinity, y approaches infinity, so there is no absolute maximum. Now, you may be tempted to say that the absolute minimum is 0 because that is close as it gets, right? As x approaches negative infinity, the y value gets closer and closer to 0. In fact, it goes to 0 very, very quickly, except it never reaches 0. So in other words, for any x, this thing is impossible, okay? This never happens. The exponential function never becomes 0 in its value. So even though it gets really, really close to 0, and you can say 0 is a lower limit, but it's not the absolute minimum because there's no point x where this y value 2 times e to the x becomes 0. But it gets really, really close to it. Asymptotically gets close to 0, but there is no absolute minimum. Very important point. Okay, so keep that in mind. Okay, let's go to 10. Now 10 has the answer that can vary. You are supposed to sketch one function, f of x, that has the following criteria. Let me go ahead and write this down. Write all the criteria down, so I can write really fast. Okay, so I have to find one function. I have to sketch the graph of one function, fx, so that its domain is -3 to +3, and so on. Every one of these things has to be satisfied. Okay, I'm going to sketch the xy plane. So let me give me a moment. Okay, so I have the x axis and y axis, and on your exam, I'm sure you will have to draw these sketches. So make sure you indicate your x axis and y axis. These two axes have to be in this orientation, of course, the typical XY plane. And then the first thing it says is the domain is from -3 to +3. Okay, so you should clearly indicate these points. Part B is very nice, right? Because it gives you at least 2 points. It does give you the beginning and end points of this graph. F of -3 has to be 1. So -3, 1. And 3, -1, these are 2 of the points. And in fact, these are the 2 endpoints. Now the graph, it doesn't say that the function is continuous, but from everything else we see here, the derivative is defined and the second derivative is defined, seem to be defined at every single point. And so you know that the function should be and must be continuous. Now, what does C tell us? You need to know how to interpret these things. This says, well, the derivative is positive. That means it's increasing. So from here to here, -1, the function has to be increasing, and then from 1 to 3, it has to increase. So technically, you start here, it has to go up here, and then it also has to be increasing from 1 to 3. But then between these, -1 and 1, it has between -1 and 1, it has to decrease because the derivative is given as negative, some negative number. So basically the graph has to look like this. Okay, now I haven't graphed this yet because I don't know what the rest of this looks like. Okay, but graph in general has to look like this. All right, and then the next thing, the part D says the second derivative is negative from here to here. So that means it's concave down. The second derivative is positive. On the other half, the concavity half has to be up here. So with all of these in mind, you can probably picture something like this where the concavity is down and it has to reach its highest point at when x is equal to 1. Okay, and it starts to decrease sharply. It doesn't have to go to the origin, but I guess why not, right? Because then this point has to be an inflection point. You should indicate that somehow. And then goes down. It doesn't, again, it doesn't really matter how far it goes. You can keep going here, but it has to start to turn this other way. And it has to be the lowest point here. And it has to go back to 3. Now, notice here, I can't go straight like this. I can't even go this way, right? I have to go, because concavity is up, I have to make it smooth like this, where it's getting higher and higher, or the slope is getting greater and greater. So this is an example of this. It does, sorry. I can't go to that. I have to go to this point. So that means my function has to look like this, okay? It has to end at 3, -1, and it has to start at -3, 1. This is the lowest point. This is the highest point. And, you know, because it has to be increasing here, it has to be increasing here, and it has to be decreasing here, right? So that is an example of a solution for number 10. And this segment will stop here. And then in the new segment of this video, we'll start at number 11.